In this video, we want to take a look at some examples of solving separable differential equations. Recall that a separable differential equation is a differential equation that can be written in the form y prime equals f of x times g of y. In other words, we're able to write it so that the derivative of our function y is equal to a function entirely in x, f of x, multiplied by a function entirely of y, g of y. When we have a differential equation of this form, we can solve it by moving all of the y terms to one side of the equation and moving all the x terms to another side of the equation, and then integrating both sides with respect to the given variable. In our first example, we want to solve the equation y prime equals 6x squared over 2y plus cosine y with the initial condition y of 0 equals pi. We first note that this is a separable differential equation. Our f of x, as we called it, would be the numerator of our expression, 6x squared. That's a function strictly of x. And our g of y is 1 over 2y plus cosine y. So g of y here is not just the expression in the denominator, but it's the fraction of 1 over that term, which is a function strictly of y. And so being able to write the right-hand side of this equation as a function of f of x times a function of g of y, we know that this is a separable differential equation. So in order to solve it, our first step is to rewrite our derivative y prime as dy dx, and this will allow us to artificially separate our differential, our derivative dy and dx, so that we can get the x's on one side and the y's on the other. In order to do that, we can multiply both sides by 2y plus cosine y, the denominator on the right side. And we'll go ahead and multiply that by dy over here. And we're also going to multiply both sides by dx. And what we're effectively doing here is moving all the y's to the left side and all the x's to the right side. Once we have that done, where the variables are split up, we can find the antiderivative of both sides. In this case, these are all elementary antiderivatives. So an antiderivative of 2y plus cosine y is going to be y squared plus sine of y. And on the right side, we have 6x squared, and an antiderivative of that will be 2x cubed, using the power rule. And of course, we have our arbitrary constant plus c that we can add here to the right side. Now, next step in solving these equations is, if possible, to solve for y. However, on the left-hand side here, we have a complicated expression, y squared plus sine of y. And with that complexity, there's really no way for us to be able to solve for y from this equation. And so the only option we have in this case is to sort of leave our solution as an implicit function of x and y. So we're going to have a solution that has the form y squared plus sine of y equals 2x cubed plus c. We want to determine the exact value of c that satisfies our initial condition of y of 0 equals pi. And so we're going to substitute 0 in for x and pi in for y and solve for the constant c. So when pi is substituted in for y, we get pi squared plus sine of pi. And 0 will be substituted in for x, so we get 2 times 0 cubed plus c. And this simplifies very nicely. We know that sine of pi is equal to 0. And so the left-hand side here is simply pi squared, and the right-hand side is simply c. And so we get a constant here of pi squared. And so our final solution to our differential equation, which is an implicit function, will be y squared plus sine of y equals 2x cubed plus pi squared. And this will be our solution to our differential equation. If you'd like to try a similar example, pause the video and solve y prime equals e to the x cosine y cotangent y with the initial condition y of 0 equals 0. Resume the video and the full solution will appear in a few seconds. because we can write the function as e to the x times cosine y cotangent y, we are able to see easily that this is a separable differential equation. So we rewrite y prime as dy dx and rearrange the equation algebraically so that all of the y terms are on the left side and all the x terms are on the right. Here we end up with 1 over cosine y cotangent y dy equals e to the x dx. And 1 over cosine y can be rewritten as secant y, and 1 over cotangent y can be rewritten as tangent y. So our left-hand side is secant y tangent y dy, and that's equal to e to the x dx. We antidifferentiate each side of that equation, and we end up getting the secant of y equals e to the x plus c. If we wanted, we could easily solve this equation for y by taking the inverse secant of both sides, and we would end up with y equals the inverse secant of e to the x plus c. And this would be perfectly fine. However, we're going to leave it as secant y equals e to the x plus c for purposes of finding c. With that equation, we substitute in our initial condition, y of 0 equals 0, so both x and y will equal 0. We get the equation secant 0 equals e to the 0 plus c, which simplifies to 1 equals 1 plus c, or c equals to 0. Once we know that c is going to equal 0, our final solution can either be written implicitly as secant y equals e to the x, or again, we could solve for y, and in which case we would have y equals inverse secant of e to the x. In this example, we'd like to solve the equation secant x times y prime equals e to the sine of x minus y with the initial condition y of 0 equals 1. In order to get this into the sort of standard separable differential equation form and to be able to use the strategy for solving separable equations, we need to do some algebraic bookkeeping to be able to rewrite this so that we have a product of x multiplied by a product of y. So when we do this, the first couple things is to rewrite our differential as dy dx. We're going to want to do that at some point. And on the right-hand side, we're going to need to do something with the e to the sine x minus y. As written, this is a single term, and it involves both x and y. And in order to use the separability of the equation, we need to be able to rewrite this as a product of something in terms of x and something in terms of y. And so here we can use the standard property of exponents, that e to the sine x minus y will be equal to e to the sine x times e to the negative y. And now we have this split up as a function of x multiplied by a function of y. We need to do a little bit more bookkeeping. We need to, for example, move the secant of x to the other side. And so we can do that by dividing both sides by the secant. And so we're going to have e to the sine of x multiplied by 1 over the secant of x. And then e to the negative y, we can move again to the other side by dividing by it. So we have 1 over e to the negative y on the left-hand side. And so here we just have to simplify a few things and we will be good to go. So on the left-hand side, 1 over e to the negative y will simplify to e to the positive y. Remove that term to the numerator and change the sign of the exponents to become e to the positive y. And on the right-hand side, we have e to the sine x. And 1 over secant x can be simplified as cosine of x. And so all of our functions are now easily rewritten. And so we can move the dx part of the differential to the right-hand side. And now we have completely separated our equation into a left side of e to the y dy, which contains only y, and e to the sine x cosine x dx, which contains only x. The next step here is to find an antiderivative of both sides. On the left, that will be easy to do. We're simply going to get e to the y, since e to the y is its own antiderivative. On the right-hand side, we do need to do a short u substitution. We can let u be the sine of x, and then du will be cosine x dx. So we have exactly set up perfectly for a a substitution integral. And so this ends up being on the right-hand side, the integral of e to the u du. The antiderivative of that is e to the u plus c, and substituting u being sine of x back in, we see that this will equal e to the sine of x plus c. And this is our solution as an implicit function of y. We can make it as a function of y by simply taking the natural log of both sides. And so y is going to be the natural log of e to the sine of x plus c. The last thing that we need to do in order to solve this differential equation is to use our initial condition, y of 0 equals to 1, to find the exact value of the constant c in this solution. In order to find the value of c, we can use either of these last two equations. We can use either the implicit equation, e to the y equals e to the sine x plus c, or the explicitly solved equation, y equals natural log of e to the sine x plus c. In this case, it'll actually be a little bit easier to use the implicit equation, e to the y equals e to the sine x plus c, and so that's the equation that we'll use to find our value of c. Although, once we know that, we'll then plug it into our final solution that is solved for y. So we're going to take our initial condition, y of 0 equal 1, and substitute it into our solution, e to the y equals e to the sine x plus c. And when we do that, we get e to the first power equals e to the sine of 0, all plus c. E to the first is just equal to e. And sine of 0 is equal to 0, so this becomes e to the 0, or 1. And so we can subtract 1 and see that c is going to be the value e minus 1. Once we know that, we can substitute the value of c into our function of y to get our formal solution, our complete solution to our initial value problem. So we have y equals natural log of e raised to the sine of x power plus e minus 1. This is our final solution to our initial value problem. If you'd like to try a similar example, solve the equation y prime equals 4e to the negative y minus x with the initial condition y of 0 equals 7. You can resume the video, and in a few seconds, you'll see a full solution to this problem. So for this equation, we rewrite y prime as dy dx, and we split up e to the negative y minus x as e to the negative y times e to the negative x. We then move e to the negative y to the left side by dividing by that function, and we have 1 over e to the negative y dy dx equals 4e to the negative x. 1 over e to the negative y simplifies to e to the positive y, and we can move the dx to the other side, and resulting in the equation e to the y dy equals 4e to the negative x dx. We antidifferentiate both sides of this equation. On the left-hand side, we get e to the y, and on the right-hand side, after a small u substitution of u being negative x, to introduce a negative sign, we get an antiderivative of negative 4e to the negative x, and of course, plus our constant c. And so we end up with an implicit equation, e to the y equals negative 4e to the negative x plus c, or an explicit equation, y equals the natural log of negative 4e to the x plus c, obtained by taking the natural log of both sides. We then use y of 0 equals 7 to find the initial condition. So we substitute y of 0 equal to 7 into the implicit equation e to the y equals negative 4e to the negative x plus c. When we do that, we obtain e to the 7th equals negative 4 times e to the negative 0, or e to the 0, plus c. This is e to the 7th equals negative 4 plus c, since e to the 0 is equal to 1. And so e to the 7th plus 4 will be equal to c. We substitute that value into our explicit function for y, and we obtain a solution of y equals natural log of negative 4e to the negative x plus e to the 7th plus 4.